Here's the solution to quiz number 3 for ECE 320 for spring 22. The first problem is an ideal diode problem. Assuming ideal silicon diodes, find the voltages and currents. Now with this circuit, kind of one way to think about it is I've got diodes in parallel. Only one of these branches can be on. If the first branch is on, I've got 3 times 0.7, 2.1 volts. If I have 2.1 volts, that'll turn on the second branch and the third branch. So that doesn't work. If I turn on the first branch, I get 0.7 volts. But this guy right here. 0.7 is not enough to turn on 2 diodes, that needs 1.4. Not enough to turn on 3 diodes, that needs 2.1. So that works. So these 2 branches are off. And the voltage at V1 then is 0.7 volts. The current is 10 minus 0.7 over R. My R is 1414 ohms. Gives you 6.5 milliamps. That current's got no place to go except for I5. I5 has to match I2. So that's the first problem. The second one is a little bit trickier. Here, assuming ideal green diodes, meaning about a 3 volt drop across the diodes, determine which diodes are on or off and find the voltages and currents. So let's start, assume they're all on. So this is on, I get 3 volts at V3. This will be 6 volts, 3 plus 3. This will be 9 volts, 6 plus 3. Does that work? Well, 10 volts over here, 9 volts across R gives you, because R that I have is 1414 ohms. 1 volt across R gives you, what is that? 0.7 milliamps. Going this way. 9 volts at 3K is 3 milliamps. So that's not going to work. Current in has to equal current out. I've got too much current being drawn. So that means my assumption is wrong. Which diodes are on, which ones are off? Well, let's take the limit. Suppose this is 0 volts. Then it's pretty clear all these are off. As the input goes up, eventually V1 starts increasing. As soon as V1 reaches 3 volts, that'll turn on diode 3, and 3 volts will also turn on diode 1. So let's guess diode 1, diode 3 are on. If they're both on, diode 2 is off, in which case the current, V1 is whatever it takes to make the currents balance. The current left plus the current through this branch, V1 minus 3 over 1,000, plus the current through this branch, V1 minus 3 over 2,000, plus V1 over 3,000 equals 0. Solve for V1, I get 4.55 volts, making this 4.55. V2 is V1 minus 3, 1.55 volts. V3 is 3 volts, and that checks. I'm trying to push current backwards through V2, that turns it off. And current in equals current out, because that's how I calculated 4.55 volts, is the voltage it takes so that the current from the 10 volt source matches the current leaving. So that's problem number 2. And once you know the voltages, find the currents. ID1 is right here. V1 minus 3 over 2,000. ID3 is this current. V1 minus 3 over 1,000. Problem 3. Assuming I have a 3 watt LED and a 10 watt LED with this voltage drop and that brightness, find the current and the brightness of the LEDs. So to find the current is just the voltage. This is 20 volts. For an ideal diode, this voltage is fixed. This is 3.6 volts, and this is 11 volts. 20 minus 3.6 over R gives you the current. The brightness then is proportional. 750 milliamps is 180 lumens. This is that percentage of 750, that percentage of 180 lumens, 2 lumens. For the 10 watt LED, this is the current. Voltage over R, 3.7 milliamps. 1000 milliamps gives you 650 lumens. Is this percentage of 650? 2.43 lumens. Problem 4. If you saw this on the oscilloscope or in circuit lab, what's the DC voltage, AC voltage, and frequency? The frequency is 1 over the period. The period, peak to peak, is 2.5 milliseconds. 1 over that is 400 hertz. The maximum is about 14.04 volts. Minimum is about 13.68 volts. Take the average of the two, that's your DC voltage. Take the difference in the two, that's your AC voltage. In units of peak to peak. In AC, you got to watch your units. If I take this divided by 2, I'd have the peak voltage. That's this guy, V peak. Now that's supposed to be V. If I find the RMS voltage, that'll be roughly the peak divided by square root of 2. Now, not exact, not pure sine wave. That'll be pretty close. So that's V RMS. So you got to label your answers. And in this class, we're using peak to peak voltage. That's a little bit easier to see on the oscilloscope. Problem 5 is a DC to AC converter, or AC to DC converter analysis. V1 is going to be a kind of a triangle wave, sawtooth wave looking like this. The peak is 19.3 volts. That's the 20 volt peak minus 0.7. The current then, worst case, is 19.3 divided by 70 ohms. That will give you 275 milliamps. From I equals C dV dt, this is a little bit battery. It's going to discharge as the voltage drops. The discharge then is I'm supplying 275 milliamps. Here's the capacitance for 1/60th of a second. dV would be 3.25 volts. So that's this distance. That's 3.25 volts. And that's the AC voltage in units of peak to peak. The DC voltage then is the peak minus half the AC. The DC voltage will be 17.68 volts. Once I know these two, I can find V2. At DC, it's 60 over 60 plus 10, 6/7 of that, 15.14 volts. For the AC voltage, find the impedance of the capacitor at 60 hertz, minus J26 ohms. Put these two in parallel, 9.8 minus J22 ohms. The inductor is J150 ohms. I now have a voltage divider. It's the R1 over R1 plus R2 times the input. The input for AC is this number. Gives you 0.606 volts in the same units, peak to peak. This is actually a complex number. Just take the magnitude and you get the peak to peak voltage. What the angle does is it says that V2 is out of phase from V1. I don't really care. I just care about how large is it peak to peak. The last problem is a design. Find C1 and C2 so that V1 is 4 volts peak to peak and V2 is 0.5 volts peak to peak. So again, V1 looks kind of like this. The peak will be 19.3 volts. Peak to peak is 4 volts. So the average will be 19.3 minus 4, 17.3 volts. The current then is 17.3 volts over 70 ohms, 247 milliamps. From I equals C dV dt, pick capacitor so that I have 4 volt ripple for 1/60th of a second at 247 milliamps. C should be 1030 microfarads. Once I know C1, I can find C2. This is 4 volts peak to peak. That's the AC voltage. If I assume C2 equals 0, I can calculate the ripple at V2. It'll be 60 over 60 plus 10 plus J 150.8, that's the inductor, times the input, 1.44 volts peak to peak. If I make the capacitor 1/3 of 60, 20 ohms, the ripple will be 1/3 of 1.44 volts. So I want the capacitor to be this ratio of 60 ohms, 20.78 ohms. Solve for C, and I get 127 microfarads. So that's the answer for C2. And that's quiz number 3 for ECE 320 Electronics 1 for spring 2022.